Thank you for joining today. It's a real pleasure to share with you what can be done on Cerebras systems. I'll start talking about a very high-level overview of who we are and what kind of hardware and software solution we provide. And then, as Murali mentioned, there will be kind of deep dive sections. So this is a kind of two-day workshop. Murali showed agenda for today. Tomorrow we will continue talking in more details about training models on our hardware, have more hands-on examples, and also we'll conclude the day with a roadmap presentation of what's coming up later this year. So with that, let me just dive in and start talking about who Cerebras is and what do we build. So for those who doesn't know us, we are a startup company founded in 2016 with a goal to create a completely new type of hardware, specially designed for training neural networks. So back in 2016, there was no transformers yet, but it was already clear that most of the neural networks required the compute, which is beyond capabilities of a single chip. So we set on a mission to create a completely different hardware solution. We all understand that large-scale AI and HPC has tons of potential. Many workloads are very complex, time-intensive, and also iteration time matters a lot. So for researchers, it matters a lot how long do you spend in distributing a run across multiple devices. It's not only end-to-end compute time, but also how long does it take for you to prepare all the experiments and make sure that your computational workload actually runs. So we decided that we would like to come up with a solution which simplifies that execution of very large-scale runs. And we will talk about what we do for traditional AI workloads, mostly focused on transformer-based architectures today, but also under the hood, our hardware is really optimized for linear algebra and in particular for sparse linear algebra. So there are some HPC applications which can take advantage from that hardware as well. And we'll have a session tomorrow to dive deeper into that. Now starting with the AI models, one of the kind of observations for today's models, they are really large and they don't fit on GPUs. So in today's world, when you program on a GPU, you essentially need to figure out, and it's typical in the developer, how you dissect and how do you fit that model and spread across hundreds of GPUs. And then after you dissect that model and spread that on GPUs, you also need to think about, sorry, not sure what's going on with the animation here. How do you connect back all of those nodes? And yes, there is existing libraries which help you to do so. But those libraries are quite heavy, and when you use those, you still need to understand how to distribute the training across multiple devices. You still need to decide in how many ways you want to run data parallel, model parallel, different types of model parallel. You need to understand how that library works, distributed type library works, and it's at the end of the day, it impacts the time it takes you to go from a very small model, which might be written just for a single device, to larger models. So on Cerebras, we had an advantage because we've started designing our systems and our clusters when it was already clear that the models are becoming that large. So for developer on the Cerebras, you never have to think about the distribution on us. We have disaggregated memory and compute on our clusters, and that memory component of the cluster can scale up to very large volumes. And what it means that essentially you can feed model of any size on accelerator, any number of accelerators. You can feed doesn't mean obviously that you can train something like a multi-trillion parameter model on a single device. You could run several iterations. It will take quite long, but it's still very useful because it helps you to simplify the development. You can start with a profiling or testing your code on a single system, even for a very large model. And then as you're ready for a larger run, you can distribute to a much larger cluster. So this kind of productivity is what matters for us and what we believe is a really important artifact of this disaggregation of compute and memory. So kind of trying to summarize what we do at Cerebras, we've started building AI accelerators. So we have a very large team. Then we also combine multiple of those accelerators into clusters and build essentially AI supercomputers. Our own national lab and our ALCF facility has a cluster with 2 nodes, but today we also have clusters, much larger clusters up to 64 nodes, and we are right now building even larger clusters in some data centers. We train models, obviously focusing mostly on large-scale models, large generative AI models, ourselves or for customers. And as a result, because we've trained several of those models, we also have in-house ML expertise, so we know how to run those very large models. The cornerstone and the heart of our solution is a very large processor. We call it wafer scale engine. That's the only processor which is built on the entire piece of silicon. We built the largest chip in the world. It's roughly 50x times larger than a GPU. Today, we've just released the 3rd generation of the chip. ALCF has systems with the 2nd generation of this chip. It's tailor-made for linear algebra, essentially, but because it's so large, it's a really good fit for large-scale generative AI workloads. It outperforms all of the other chips across all key dimensions. You think about memory cache on chip, and when we talk about cluster, also memory in the system, and compute power per one device. So it's faster. What's also important is easier to use in terms of distribution. I mentioned we paid a lot of attention making sure that you don't spend time thinking about how to distribute your workloads across multiple devices. So because this chip is so unique, we also needed a unique chassis and unique system to deliver power, to cool it down, to bring data to the wafer. So Cerebras CS system, we've started from the 1st generation, and now CS2 and CS3s are available, look like this. And you can think about that as a kind of mini fridge size system, which fits into a standard data center and powers one single wafer scale engine. So we have one card, one chip per system, and then we cluster multiple of those systems together. Previously, I've mentioned that we also have some off-chip, off-system memory. So when we cluster those systems together, it's not only the CS2, CS3 accelerators which we cluster together, we add some additional components. And one of the key components there is what we call memory X. This is scalable independently memory, which is attached to the cluster of these devices. And SwarmX is an interconnect fabric which enables us to connect MemoryX to CS systems and also to connect multiple CS systems together. In terms of the memory, we can scale it from 128 gigabytes with our standard CS2 deployments up to 1 petabyte with the larger CS3 clusters. SwarmX can connect multiple CS2 and CS3 devices. The topology of SwarmX is slightly different for CS 2nd generation, 3rd generation systems. So we can scale up to different numbers of systems in a cluster. And when we set up a single CS2 system, delivers 62 petaflops of sparse AI compute and can be scaled out with multiple CS3s up to hundreds of exaflops. And also because, again, we scale memory and compute independently, we can run models sub-millions, so hundreds of millions, tens of millions. We do often those small-scale experiments, and you can scale it up to much, much larger models. The nice thing about these kind of clusters, when you compute all of those systems together, it looks to you as still just a pre-logical components. So we have memory, which hosts model parameters, optimizer states, and does gradient updates. We have some interconnect, and we have this collection of accelerators, which can be referred to kind of as compute. And as a user, you actually never need to think about distribution. You never need to think about how many systems are behind the cluster, behind the user node of the cluster. So as an ML developer, you always code your model as you would do that for a single device. Doesn't matter if it's a smaller model or larger model. If you want to run it on a single device or larger device, the code looks always the same. And from outside, you can think about the cluster as kind of one single big device. and no matter size of the model, no matter size of the cluster. And that, at least in my opinion, makes it really convenient to do very large sweeps of different experiments which are required to get high quality models. So typically, if you want to scale models on GPUs, and if you want to go from a smaller model for some maybe initial experimentation to a larger model, you often need to change your distribution parameters. You need to change your batch size. You need to rely on different approaches to distribution as you go from sub-billion parameter model to hundreds of billion of parameters. And it makes it harder to go back and forth between smaller and larger models, which we believe is important to get to high quality models. And on Cerebras infrastructure, it's the same effort. So it's very straightforward. And later on, it will show you how to change the model size. It literally, you change just dimensions of the tensors in your code, and that's it. So you don't need to think at all about distribution. And again, this makes this preparatory work and that exploration work before you're ready to launch your very large training job so much easier and so much straightforward. We like to say that on GPUs, kind of small models are default. And then in order to train a large model, you need to think about distribution. It takes a large engineering effort. And on our systems, large models are default and small models comes for free. With this infrastructure at Cerebras and with some of the customers, we've trained a large number of different models. Some of them are open sourced, not all of them are open sourced. On this slide, I have a collection of open sourced models and data sets, just to give you an idea what kind of models we have been training. All of them are examples of transformer style architectures for different domains, just language models or code models, or family of models exploring the scaling laws, models for healthcare domain, either fine-tuning or training from scratch. And for training these models, we typically use all the kind of latest ML techniques and recipes. And this infrastructure makes it possible for us to iterate really quickly with all of those latest techniques and transformers to train state-of-the-art models. I think one specific thing that I personally really proud of for the team is that every single model that has been trained on our architecture at the time of the release was state-of-the-art at that particular size. And I attribute that to the ability to do this small-scale experimentation, hyper-parameter tuning easily on the hardware, which enabled us to kind of bulletproof the recipe for the final training run, and which enables really good quality of the models. And I'll talk about some of the examples of those small-scale experiments and how we use this preparatory work to achieve state-of-the-art models more tomorrow. But to give a little bit more details of what kind of things we are running today, just to flip really quickly. On the previous slide, you've probably seen one of the models, MED42. That was a very interesting example. That was a very rushed turnaround. We got a customer who asked us to fine-tune Llama 270 billion on a medical data set of question and answers. They wanted the results, and they wanted the resulted model really quickly. So we essentially took us a week to do from nothing to fine-tune model. Within that week, we did a little bit of hyperparameter tuning on a smaller version of the Llama. We did data set conversion into the format which is suitable for ingestion in Cerebras systems and which is high performance. So we know that we can ingest the data at a rate which won't starve the accelerators, and we essentially run the training job. And at the end, we met the objective of that team to pass USMLE exam with the resulting model, which again, that was the first open source model which can do that. Another example, and in general, we experiment a lot with the language models and multilingual models, both considering training from scratch and continuous training or adaptation of existing models. So this work has been done together with the Barcelona Supercomputing Center. Later, in late 2023, we released a state-of-the-art Catalan Spanish English model, which has been adapted from Bloom. So there have been some special techniques used to change the vocabulary to make it specific for Catalan and Spanish, reduced also the vocabulary to make it less intensive for inference, and continues to train that on that language data set to get state-of-the-art model. We also have a very long history working with the Arabic language models. So we've started with the monolingual Arabic models, and we've trained bilingual English-Arabic models. And today, the series of JACE models holds also the record of being state-of-the-art models in Arabic English. So I have tons of expertise projecting what quality you can get out of the model, what size of the model makes sense given the size of the data set. Again, we'll talk about that more tomorrow. Language is not the only type of data that we've been playing with. We also have several examples where we train sequential models on biological sequences. So this is on the slide, one of the very first models we've trained back even on the first generation system with Glasgow-Smith-Klein. That was a model trained on DNA and epigenomic data combined. So we feed DNA sequences and corresponding epigenetic sequences into the model to get good representations for different types of tissues. Again, this is not the only model we've trained on biological sequences. We are training also right now models on kind of DNA, RNA, protein sequences, and have some expertise doing that. And overall, believe that the hardware and software has great support for those types of models. In addition to ML, there are also several examples of interesting work done in HPC community. If I have to summarize for HPC, if you have an application which relies on sparse solvers and iterative solvers, those can see significant speedups on our hardware due to very high memory bandwidth and large cache. So with Total, we've done iterative solver, which has been used for reverse time migration application, and seen significant speedup versus a GPU. KAUST, similar type of application, slightly different shape of stencil, but under the hood, very similar computation also has been shown very good acceleration compared to other types of the hardware. And peers and Argonne National Lab, your peers, also has used our system to recently develop an algorithm for Monte Carlo particle transport, which has also demonstrated significant speedup compared to GPUs. So overall, I think more and more people are starting to look at our hardware and use that for different research purposes. So hopefully you can do something interesting on the system too, and help us to increase this plot, which we are proud of even further, to get more interesting work done and published on the systems. So thank you for this opportunity to present you our system, and we are happy to help in any way we can to kind of make you productive on this new type of accelerators. So with that, I will pass to Sylvia to dive deeper into hardware and programmability.